Good evening all, and welcome to this evening's webinar entitled Extending the TI84 with Apps. And this webinar is hosted by Texas Instruments Australia. You are now seeing a picture of me, I hope, if we're doing the screen sharing. My name is Brian Lannon, and I've been having a lot of fun with various platforms of Texas Instruments calculators, and I must say the TI84 was one of my very, very favourites, which really got me into using handheld technology in the 1990s. Now, during the webinar, we will be switching to your presenters shortly. You will be seeing their desktop instead of mine. And you will be hearing from Ray Cross and Jim Lowe, both from Queensland. And while you hear from them, can I encourage you, please, to ask questions? You can either use the Q&A box or you can use the chat space. Now, rather than direct your questions just to me, the host, can I encourage you instead to direct them to all panellists? If you do that, then we all get to see it, so whoever is free at the time may respond to your question. If you're watching this live rather than the recording, then you have the advantage, of course, to ask questions. Guess what? If it's a recording, that's probably not going to happen. You can ask if you like, but you may not get a live answer. Your sound shouldn't be a problem coming through your computer, but if it is a problem, then you can dial in. If you choose to do that, there's the toll-free number in Australia, and you will then be asked to note in your meeting number, and you will get the audio over your phone. All good fun. If you do switch applications while you're watching the webinar, you can switch back to it. It looks like a little globe. And the company's name is Cisco WebEx, so when you click on the globe, you're back watching the webinar, which will, on most occasions, be the presenter's screen. Now, the first presenter that you're going to hear from is actually not Ray Cross. Ray, you will be hearing from in the webinar. Now, Ray has done a range of things. He's now living the good life as a retired maths teacher. But he's taught for over 40 years, so he's done his time in both Victoria and Queensland. He's been author of textbooks, and I have seen his sessions and at the MAV and Queensland Maths conferences. But before you do hear from Ray, you will be hearing from Jim Lowe, currently at Queensland University of Technology, and you see the graphic there, where among the various things that Jim has done in his passion for bringing mathematics and science to life, particularly through data logging. He was instrumental in setting up data logging experience at Dreamworld in Queensland, and years ago I was lucky enough to be one of the participants in that. It is fantastic. If you've ever been on the big drop or the big roller coaster there wearing accelerometers, then you can read some really interesting data afterwards. I didn't strap on one that measured my heart rate, but I'm thinking that would have been a good one to do as well. Now, our presenters this evening are going to be showing us some interesting things with apps on the TI84. You might have apps on your iPhone or Android device. Guess what? The TI84 had apps way before then. They had apps even before there was an iPhone. So this will be good fun. Jim's going to be showing you, and I've seen their notes in advance, some information and activities on the Inequalities app and transformations. Ray will be telling us about Conic's Polynomial Roots Finder and possibly simultaneous equations, depending how we go for time. Then it'll be back to Jim demonstrating some things that can be done with the Polynomial Simulations app. All very good stuff. So, Jim, I'll hand over to you first.
Okay, thanks, Brian. Just getting organised here and hoping that my screen's coming through to be shared, which, judging by the change of colour, I hope it is.
It's on its way.
Yep. Okay, so as Brian said, we're looking at extending the capacity of our TI84s with the apps that are available for this device. So let's get straight into it. And why isn't that screen wanting to change? Let's do it this way. So we've had all the introductions. I just want to point out to you before we start that if you have a TI84 calculator and you are missing some of the apps, or you want to check out the full range of the apps that are available, then if you go to the education.ti.com, the Australia and New Zealand site, and click on the products and go to the TI84 page, and then go to the applications tab, you will find there listed all the apps that you are available for the TI84 CE, and there's versions of these available for the older TI84 models as well. You can download the app and also the guidebooks to instruct you how to install it and use it on your calculators or software emulator, as we're doing tonight. But our purpose tonight is to illustrate some of the features of the apps, and the best way to do that is to look at some examples of some of the things that we can do with students and point out the features of the app as we go along, and that's what we're going to do. So I'm going to get straight in, as Brian said, with the Inequality and Transformation Graphing app. And I'm going to do the two of these together for a very good reason, in that they work similarly. When you install and load these apps onto your calculator, you will find that they enhance the features that are already available. So if you're comfortable with your calculator drawing graphs using the y equals key and the graph key, you will find that installing these apps gives you some additional features, and it's those additional features that we're going to look at tonight. So looking at the Inequality app first, from your calculator, if you click on the apps button, you will get a list of the apps and you will see inequalities there. Now, I should point out for any people that are not too familiar with the apps, mine there you can see that the application is number 5, and I can get to that either by using the arrow keys or by simply typing the number 5. But if I change the apps or install new apps, it may not be number 5. And if you've got a different combination of apps on your calculator, so you're just going to have to scroll through your menu and find it. Don't assume that it's automatically going to be number 5, and that goes for any app. So when we install that app, we're going to have a look at it in a moment, but you will see that your y equals screen has changed somewhat. We've got a few extra options along the top, and the left-hand side looks a little bit different. And if you look up at this little graphic here, you'll see that we've also got the ability to plot graphs to the form x equals, right? And here's the result with the shading and so on. So let's have a look at that, and let's bring up the emulator and have a look at that. And so there's my y equals screen. As you might expect it, I've got a graph in there, y equals 2x, and you may be aware that you can take your cursor over there and scroll through, go through a number of possibilities there to change the style of the line that you've got there, and that includes some possibilities for shading above or below the line, and also how it's represented. And so we're going to have a little look and see how the Inequalities app enhances that capability for us. So I'm going to click on the Apps key, and as we said, Inequalities is number 5. Up comes the app, press any key, so we'll press that one again, and there's my graph, y equals 2x, I can graph that and have a look at it. I happen to have my window set for the upper part of the coordinate plane. That's okay. Let's go back to y equals and see what we can do over here. Now, when we press enter to go into that, we've got this extra option that comes up there. So I can change the colour of the graph. We won't get into that now. But click down to go to the next option and use the left and right arrows to cycle through the options. So if I want, instead of y equals 2x, I want less than or equal to that, I can see how it's going to be represented. Or if I just want, where's my cursor gone? If I want strictly less than or greater than, you can see that we've got the dotted line option for the boundary. Go down there and click on OK. And now when I go to the graphing plot, there's my what y is greater than 2x graph with the boundary in the dotted form because it's not included in the region. So that's a quick rundown on what you can do, but there's a few extra features in there, and so let's have a look at some of those by looking at an example. Now, quite often what we're doing is with inequalities is looking at linear programming type problems, so we've set up one here as an example. It's not our purpose tonight to go through linear programming in detail, just to use it as an example of some inequalities to graph with a purpose. And so, yeah, this is actually somewhat realistic that I happen to know a retired teacher up in Toowoomba that makes his living from selling these things now. I don't know if he's ever done linear programming to work out how much of these to make, but I formulated a problem based on what was on his website and his advertising and so on. So we've got two things, our jumbo and our space saver. We've got a few constraints. So let's have a look at the graphs and see what we can come up with. So first of all, let's define that x is going to be the number of type A and y is the number of type B. We've got some constraints, and so that's going to be in the form 2x plus 3y is less than or equal to 30 because we've only got 30 hours of machine time available. We've got 60 hours of craftsman time that we can represent like so. And we also going to make the assumptions that he's going to make at least some of each type of machine, and the typical problem that we would be trying to maximise the profit that he's going to make for any given day, assuming that he can sell these things as well. So that's what we're working on. So let's have a look and see how that's going to work on our inequalities graphing machine. Let's go back to our y equals editor and see what we're going to graph in here. And we need to, of course, change the equation around. So I'm going to get that here y is equal to 10 minus, whoops, go back over there and delete that one. I knew I shouldn't have, whoops, too far. 10 minus 2 thirds times x. Okay, well now I've got 2 x's. I'm getting a little bit of a lag here. Sorry about that. It's disconcerting. And we'll go down and pop in the other ones here. That's going to be y is going to be 12 minus x. And x. And then the other one we've got, of course, is y is going to be greater than 0. And so I've just put the equations in there. Now I can go across and click enter and go down and decide I want that to be strictly greater than 0. So that one's in there. Okay. And I want that one to be less than or equal to those values. So we're wrong way, less than or equal to, enter, enter, and likewise I want that to be less than, oops, still went the wrong way, less than or equal to. Okay, and so when I go to my graphing screen now, I see the equations graph, and we've got that there. Now, the one I haven't graphed is the one about x being greater than 0, and so if I go back to the y equals, you'll notice that I can now go up to here and click enter on that, and it turns it into x equals, and x is equal to 0, and go across there and turn that. I now want that to be x to be greater than 0. And it doesn't matter, I don't have to go back to the y equals. I can simply go to the graphing screen, and it'll be a little bit hard to see because obviously we've got other things going on top of that there. But one of the things that we want to point out that is extra in this thing, if we go to our second function now, those are our normal things that we get in the calc menu, but we've also got this new inequality thing popping up here. And so I can arrow across to that, and you can now see that I have these other options for the intersection and the union of all these areas, and another thing called this point of interest trace that we'll get to in a moment. But I'm going to go for the intersection of these areas and click on that and let it graph over the top of that, and you'll see that it's progressively wiping out bits as it draws other graphs, and I now have a region for my curve. And if I went in there and reset my window, normally you notice that we've got an extra little menu item popping up here in the Windows settings one. That is the shade resolution there affects the density of the lines that are shading the region. So I tend to just leave it on the standard shading all the time because we're not worried about the style of shading. We're just interested in that we can use the colours for that. Very quickly going to change this to -5 down to 15, and hit enter for that one and go back to the graphing one. Oh, I changed it the wrong way. What did I do then? Silly me. Anyway, there you can see what happened there. I changed it to
-50.
Yeah. Okay. And let's try graphing that one now, and it might look a little bit better for us. And we get our region appearing for us. And what have I done there? Should have got that less than, greater than, x equals, graph. Oh, okay. I've got out of it and changed the settings, so I need to go back to the inequality menu and change it to the intersection of these areas, and now it will do it for me. And now we're wiping out bits as we go and leaving us with the region. And so very quickly to finish this little section here, because Ray's got quite a little bit to do, but the other one that you can do in this thing with the inequality options is look at the point of interest trace. And those that are familiar with linear programming would know that that function that we are trying to maximise will be at a maximum somewhere at the boundary of the region and on the corners. So now when we use the trace key, it will, don't need to do the trace key, I needed to do my mistake. See what happens when you do a webinar, you forget everything, right? Point of interest trace, and then I can just use the arrow keys to cycle through them. And if you look at the menu up the top, if I use the up and down arrows, it can change the functions that I'm working with. And so I've now got Y2, I've got the regions, I've now got x1 and y1, so I'd be looking at the intersections of those, y3 and y1 and so on, so that as I go through now I get different points of interest in the region, so that eventually if I swap the functions up here I can get through to all the different points and get the values of them from down here. So that's a very quick look at the inequalities. I might just say a couple of things about the transformation graphing app and then hand over to Ray, otherwise we're never going to get finished tonight. The transformation graph or transformation app works in a similar manner. It enhances your y equals capabilities and allows us to put in a function with parameters here, and we can scroll through and change these parameters so that we can actually fit the curve to some data plot points there. And you would notice that both in the inequalities and in this transformation app, we can turn on and off the stat plots from our y equals menu so that we can actually see a set of points, draw a graph and fit it to the curve. I was going to do an example of that, but I think at this stage, Ray, I might hand over to you, and if I get time at the end, we might come back to this one. How does that sound?
Yeah, that's fine with me.
Yep, go for it then. You've got quite a bit to do.
Okay, so let's see if we can just share this screen. Doesn't seem to be coming up as yet. Bit of a delay obviously at the moment. So basically while we're waiting for that to come up.
Yeah, thanks Jim, and as we're just handing over to Ray there, that works so well I think, particularly in the colour. When I was talking before about using the TI84, well actually it was the TI82 and then the TI83 in the 90s, we didn't have the colour. And now that the latest version of the TI84 plus CE does have that, I think it just really takes it leaps and bounds to another level with what you can do with it. Can I also just point out, with the Inequality app and also the Transformations app, students, when they get the new calculator, they love to explore. They're just right into it. And they switch on all these things, and they will still run in the background. So next time they press the y equals key or the function editor, they've still got those commands and that format happening. It's a very common one when they ask the teacher, what's happened to my calculator? Just look for that. Go in, press the apps key, go into those ones and then switch them off individually.
That's been handy.
Good point.
Handy tip.
On my list, but I just forgot it.
Yes. So Ray, I saw what Ray was showing us before. This is very exciting. So stay tuned. Ray, tell us about it.
Well, we're set to go, so hopefully we'll get through Conics, have a look at Polynomial Root Finder, and maybe, although I doubt it, somehow get into Simultaneous Equation Solver. But I thought what we might do to start off with is look at a polar ellipse, and obviously one of the most famous ones often talked about is the elliptical orbit around the Sun. But oddly enough, I've never actually calculated what the eccentricity is, so I thought we'd have a little look at that. So you can see on the screen on the left there's part of the PowerPoint. What I'll do is just enlarge that by putting a little Word document in there. So it's the same one, and at the moment it's the aphelion, or pretty close to it in a month, will be 152 million kilometre from the Sun, which is the focus of one of the elliptical orbit, 3rd of January, 147.1. So what we can do is these distances RA and RP for the perihelion. What we can do is calculate the semi-major axis length. So we'll do that quickly by putting in 147.1, add to that our 152.1. So if we just, hang on, got a mistake there, we have to add that. So add that in, And then if we just delete that one, that gives us that value there. We've got to divide that, of course, by 2, and that's our semi-major axis length. So I'll store that to be A, and then to calculate the semi-minor axis length, the way to do that's pretty straightforward. Most of us will be aware of that. So we just look at the square root of A, and we're going to take away from that the value of A minus L147. What happens? Minus L147.1, bracket that, square that, and what we get there is the semi-minor axis length. So if we store that one to B, and from there, with those two values stored, we can set about working out the eccentricity, which of course is the square root of A squared minus B squared, and we just get out of that one, and we've got to divide that by A. So we come up with the eccentricity of this thing, which is very, very small. Obviously, it's pretty close to being circular, so how Kepler got away with found out the orbit is just quite incredible to me. So it's really, really circular. So having got those values now, the other thing we need is the distance between the focus and the directrix, and that can be calculated by looking at A divided by E. So we get that, and we take away from that the focus. So that's the directrix in there, and we take away the focus, which is A multiplied by E, and that gives us that distance. Now, the peculiar thing about the app, for some reason or other, which I don't understand, is instead of using that distance, which is usually used in the polar form of conics, the app uses half of that value. So you've got to divide that by 2. So how do you get the app? Just as Jim was showing, get into app, be careful about where it is, don't assume it's the same number, and in this case it's number 4, which will be the case for most of us, I guess. Down to number 2, which is the ellipse, we need to check the mode, and it's going to be in polar mode, so you can just scroll backwards and forwards there, but we've already got it set in mode. Down here is particularly interesting. You can use auto or use manual. I'll just use auto on this occasion, and then when we do the next one, we'll do manual. I rather prefer to use manual because you've got a bit of control over Windows settings and can play with them a bit, look at the scale and so on and so forth. So for that, let's just use auto at the moment, and then we go back here. What do we want? This one seems to me to be a pretty suitable one, so just press enter, and then in here we need to put our eccentricity and our p-value. This p-value, as you see from the equation, is you normally have ED up there, so it's half of the value of the distance between the directrix and the focus, as we just calculated before. So I've already got P in there, so we'll put in our value for the eccentricity, which I remember was equal to that. And the unfortunate thing also is you can't actually import the stored value for the variables. So it'd be nice if you could do that, but you can't. So I can't simply type in alpha E there. So then the big advantage of this is that you can look at the characteristics of the conic, and to do that just press alpha and solve, and it throws up the centre. One of the foci, of course, is at the origin, which is this one here, 0, 0. There's the other focus, and then we can graph it, and once it's in auto mode, it throws up the graph straight away. We can do a trace and just press right or left and trace around the thing. You just can't, in this mode, change the window, and that's why I tend to prefer the auto change to a manual, so you can have a little play with that, and you can zoom in and zoom out, which you can't when you're in auto mode. So that's a little bit of an example of how we can use the conic to determine the orbit of the Earth around the Sun. So on the documentation you'll get, there's another example there that you can have a little play with. The next one is one
So close to a circle, it's...
oh, it is.
Yeah,
Right, so
but that's because of that low eccentricity value, isn't it?
Oh, extremely low. You know, 0 being
Yeah.
a circle and 1 being a parabola. It's just incredible. So the next one we'll have a look at, again, is something that you see all the time. It's in just about every maths textbook on conics, but for some reason I've never actually done it, so I thought I'd have a bit of a go.
I love the source of your data there. That's great.
Yeah, well, I just sort of managed to, much to the concern of my wife, managed to find a lamp, and this particular lamp was not the usual sort of cylindrical one. It was a truncated cone. The top of the lamp was 14 centimetre in diameter. I actually did all this, and the bottom was 18 centimetre in diameter. The light bulb was around about at the centre of the height of the truncated cone lampshade, and the total height of the thing was 26, so therefore halfway through is around about 13. So what we've got to do there is look at establishing the equation. So what I'm going to do is just a little bit easier to look at a Word document here. So I'm just going to come in here, and there's the same sort of data, and this is the setup that I used. I decided that the z-axis would be normal to the xy plane, and I thought that was the simplest, that I was going to try and determine the equation to the hyperbola in the xy plane, with z being normal. And so the cone, a truncated cone of the lampshade, will have running through its centre the y-axis. So if you understand the way in which it works, that's the normal to the plane of the shadow. So down here, just done a couple of quick calculations down here, which hopefully you can see. I might just enlarge that a little bit. Basically, the equation for the cone in 3 dimensions is x squared on a squared plus going to use z squared on b squared is equal to y squared on c squared, and we set the denominator of x squared and z squared each as being 1. So what we have to do is work out c, and so we choose a point, and those of you looking at that can see that I've done it in the Inspire calculator, and I actually did this diagram in Inspire as well. And so we're going to choose this point here, which is 0 for x, and it's 13 for y, because that's the height of the top of the lampshade from the light source, which is there. And then the distance along the z-axis is going to be 7, because that's half the diameter of the top of the lampshade. So you pop these values of 0, 13 and 7 in, and you can evaluate c as 13 on 7. And then since I placed, as you see in what I've got here, I placed the lampshade flush against the wall. It meant that the larger of the two ends, that's the bottom with the diameter of 18, was against the wall. So it was 9 centimetre, therefore, from the y-axis. So if we put in z equals 9 and then just change the equation around, divide by 81, we come up with the equation to the hyperbola in Cartesian form. So going into the apps here, we just have to get out of this one and escape from that, escape from there. So now we want to do number 3. We're going to have a look at hyperbola. In mode form, we're looking at function, and as we mentioned before, we're going to have a look at manual, because I'll show you how we can fiddle around with that and make things a little bit better. So then the form that we want, well, obviously it's number 2, which I'm certain everyone understands, and the A value in this example is equal to 13 multiplied by, well actually it's 13 on 7 I think, so we'll just change that 13 divided by 7, that value of A? No, it's not right. It's 13, actually I was right the first time, 13 multiplied by 9 and divided by 7, so if you take the square root of that thing there, then that's what that is. So we'll enter that one. The B value is 9. H is obviously equal to 0, and K is equal to 0. So again, as we did before, we can look at the characteristics of the conic, and that gives us that. Notice down here we've got the gradient of plus and minus gradient of the asymptotes to the hyperbola. The centre is at 0, 0, the two vertices, foci and graph, and it doesn't look very good. So if you go to zoom and window, what can happen is you can do a zoom conic, which looks like that. Then if you go to number 5, zoom square, it squares it up, and it's beginning to look a little bit like the image that we had before, which was that. What you can do is change your window, obviously change the scale so you don't have all those markings on each of the scale. You might change that to 10 and come down.
And Ray, that zoom adjustment is a benefit of going manual instead of auto.
Yeah, that's the benefit of going manual, Brian, and that's why I rather like it, because you actually can't, apart from doing a trace, which you can still do on this one, of course, you can't see the scale, and I just like to do that and be able to look at the window and zoom in. I just think it's a much better thing than just seeing the axes without any scale or markings on it. And you know, you can still do a trace with this, so you can just go through it like that, which is absolutely great. You see over here, just to look at this, what I did, I actually knocked the lampshade going in. So I measured across here, it was 7 centimetre and up to a point, and it was 21.5. So if we have a look at our equation, so we'll just get out of this and see how close we go. So we'll put in, I think it would be, work this out previously, so that I didn't have to think too hard.
And that was physically measured on your wall?
Yeah, that was physically measured on the wall, yeah. Well, actually, to be honest here, it wasn't a wall. I've got a marker pen. It was an old fridge, which served the purpose really nicely.
Okay, yep, I like it.
Which I'm about to throw out. If it had been a wall, I think I would have been killed. My wife wasn't there. There's an old fridge in the garage, so that's what happened. The markings are still on there because I used a permanent marker rather. So we do 13 multiplied by 9, divide that by 7, and then take the square root of 1 plus 7 squared divided by 9 squared, and we enter that, and we get, well, we don't get 21.5, but I think we pretty well get the idea. So I think we might just, Brian, I think we might leave the parabola alone, because basically, you know, you can see how you can change the settings and the modes and all the rest of it, so people can go back in and they can do that for themselves by following the notes that accompany this webinar. So I think we might move on now and have a look at another really useful app, that being the Polynomial Root Finder. And the real advantage of the Polynomial Root Finder, I think, is the fact that you can investigate numerically and analyse numerically the number of roots, and also how you get the value of these roots, rather than just slavishly relying on plotting the equation, seeing where it intersects with the x-axis, which we all do. And it just brings another mode of analysis that's one of the advantages, big advantage, of course, of these calculators, multimodal presentation. So I think we'll look at that. So we go to number 7, and what we're going to do is number 1, the polynomial root finder. So we'll go into there, and then we're going to have a look at a cubic to start off with. So you can change those, of course, to whatever you want, but we'll do a cubic, and you can see you can have those. I'll get a chance to hopefully show you the complex mode, but we'll use real at the moment and just leave it in degree. Go to next by pressing the top there, and you can see you have the possibility in this cubic of entering all of the coefficients manually, which is a bit of a pain, particularly if it's a high order polynomial. So instead you'll notice down here you've got load, and if we just press that, I've actually already stored in a list some coefficients. You just put them into a list, and that list is called C1. So pressing number 7, I'm going to load that coefficient list. It's quite handy for high order polynomials. And load that into so it's a really simple one, just 1001. So we're going to solve that, and you can see we get one solution. Great, one solution. So then let's have a look at changing the coefficients. So we just press zoom up there, and now I'm going to load another list, and no surprises, that's going to be called C2. So press 8, load that. So I guess you can see what's happening here, that we've got this polynomial which gives us 2 answers. So obviously I don't really know why we get 2 being the same, but it does have just 2 solutions, but it seems to throw that up for some reason. And so now we're sort of looking at asking students, okay, so now we've got 2 solutions out of as zeros of this polynomial, third order polynomial.
So double root.
Yeah, double root. Yeah. So now we won't take that any further. So now let's go to change it again, and this time we'll load in C3, which is really quite exciting. So load that in, and we get that one, solve that one, and of course now we get the 3 roots. So, we're asking the question, is there a situation where there's no roots? We've already got 1, we've got 2, we've got 3 roots, so we can discuss that. But what's really important, of course, is what about the value of these roots? And we clearly think about the value of the roots of a quadratic all the time. We're doing it from grade 9, basically grade 10 in all states as J, I imagine. But the rational root theorem, something that probably we don't emphasise as much as we should, and just using a little quadratic as an example here, that all of the possible real roots are plus or minus the factors of the constant at the end of the polynomial divided by all of the possible factors of the coefficient of the leading polynomial, a leading term, which is 5 in this case. So we look at plus or minus, the factors of A are 1 and 5, the factors of C, 1, 2, 3 and 6, plus or minus that. We then can see that the possible roots are plus or minus the 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1, also those. So you've got a total of 8, and we all know if we test those, we come up with those too. So does it work for a cubic? Well, it does. You can go through and look at what you've got there and check them all out and see. whether it does or not. And probably a good way to do that is if we just quit this for the moment and just look at where these lists are. I've actually stored the lists, and of course you can do that in the polynomial root finder. And C1 is what I stored initially, and R1 is I stored the solution list. There's C2 and there's R2.
Solutions, yeah.
Yeah, and then C3, you just do an insert and whack them in. And you know,
Yep.
I think students, you could give them these lists to insert and play with initially, and then see if they can come up with how do you get these as the roots from these numbers, and get them to analyse it rather than just simply looking at the whole business of where the graph cuts the x-axis. So, and of course, at the end of the day, you can just really, if you want to, just check it by, you know, there's sort of polynomials there, graphing them, and then you can see where
But the beauty is you can look at it graphically and algebraically.
Well, that's the thing, and I don't think we look at it algebraically and, you know, you're playing with it numerically, getting them to have a look at what the factors are and extending the idea of factors of a quadratic into a cubic, quartic, quintic, whatever you like, and it works. And I just don't think we concentrate on that. So we get a generalisation of the whole thing, and you know we can ask those questions. We're beginning to get pressed for time. I'm not really be able to get to any of the other things, but I might just we might just go in here and show you that that you can actually look at complex roots. So if we go in here, we're going to turn, if you go to 4 as the order, fourth order, see what happens? Immediately it's going to generate complex in complex mode. And you've got a choice between rectangular or polar, and I won't be too long here, Jim. And so if we just go to next, you can see we can just do the entries in there. I might just put in, hang on, we'll just put in a, go down here for A0, we're just going to put in a 1. So we're looking at x to the 4th plus 1 equals 0.
Plus 1, yes.
Yeah, plus 1 equals 0. So I guess you're quickly nutting out what the solution would be. And the thing about this, which I just think takes a little while, but I just have a look at that. It doesn't generate just the principal roots, but it throws out all of them, the 4 roots. Just absolutely magnificent. And you can store them, and we just go to mode. I'll just quickly change this and
you could have scrolled across to see the eyes on that.
Yeah, you could have. Yeah, scroll across. Yeah, absolutely. And come down here, and we're going to change this to, we'll leave it in degree, I think, and then go to next. So we're going to use the same polynomial, solve it, and have a look at that. How good is that? I really think it gives you every one of the 4 roots that are applicable. You can have a look at that on a Cartesian plane. Where are they? Start asking questions. Why are they spaced as so? What's going on in this situation? How does the polar form relate to the Cartesian form, etc., etc. Now, look, we've only really got through half of what I wanted to get through, Brian. So I really think we'd better pass across to Jim. So I hope there's something in there, and over to you, Jim.
Yeah, it's pretty good stuff, isn't it? And interestingly, the TI84, it's not a CAS calculator, but look what it just did. As for the polynomial root finder array, it was my students before I did found that app or a variation of it, an earlier variation of it. As I was telling them, this can't do algebra, it's only a numerical calculator. And they said, oh yeah, really? It can do it can solve the algebra you're giving us.
That's right.
That's what the kids will do.
Right. That's right. Yeah. You have to start thinking about rewriting the questions you're asking.
Yeah, yeah, definitely, yeah. So Jim,
Okay.
probability
Thank
simulation,
you.
one of my favourite apps. This is a beauty. I love this area.
It is. It's a great little app, and for something completely different, we're sort of transforming ourselves right down to an app that you can use with quite young students, really, because it does what it says. It's a probability simulator, and we can use it to set up situations that we would normally do with physical equipment, but let the calculator take care of the data gathering for us. So as you can see there, it's called Probability Simulator. When it opens up, you've got some options here to toss coins, roll dice, choose marbles from a barrel, a spinner, cards, and random numbers. And I'm going to have a look at a couple of examples of typical things that I do with students, or have done in the past, because I haven't had any students in the last couple of years to work with. But this is fairly typical. We've got the screen set up here. It's the first option to toss coins, and we just use the basic single coin. And so if you were running this app, you could toss one coin, it simulates it, and you get the results shown on a graph. And we could do a few more by clicking this button a few times. But then, of course, you can go to doing it 10 times or 50 times and keep on going. And what it does in those situations is you'll see it simulates tossing the coin once and then gives you the 10 or the 50 data points added
Jim,
to
I'm
your
not seeing
graph.
your emulator there.
No, that's all right. I'm getting to that. All right.
All right.
So I was just talking to the slide at the moment, yeah, and so we've got a situation set up here, again, just on the PowerPoint as an example. So I was going to make this a little bit interactive, but we're a little bit down on numbers, but it gives you an idea of the things you can do with kids if you've got something like the emulator that you can project on a screen. So you can actually use this with students and say to them, okay, there's 15 marbles in that container. What colours are they, and how many of each colour are there in the container? And then you can progressively scroll through, and we've got a red one, another red one, a blue one, and you can be asking kids to make predictions as they go through. And the way this is set up, they're going through and they're starting to make predictions about so many reds, so many blues and so on. And of course, we could be doing this with a real barrel and real marbles, but what you can't do when class time is precious is when you get to a point, you know, the kids are convinced that there's only red and blue marbles in there at the moment, but then all of a sudden C pops up, right? So you then ask the question, well, is there anything else in there? And so on, and how would we know? And that's where you can, with the simulator, make it very quickly run through to 50 or 100 type things. And as I'll show you in a moment, when we go to the actual simulator, is look at the total sample space there and the set of outcomes and see what actually happened. So that's one little variation. Rather than just using it to take the place of using the physical objects, we can actually be a bit creative about how we use it. What I want to do now is, you can also change the representation. Yep, forgot about that one. Now to this one. A little game. I've used this activity with students, and I got it from somebody at a conference somewhere and adapted it for this. I give the students this game to play. We're going to roll 2 six-sided dice 36 times. Using this with fairly young students, year 8, year 7. You score 5 points for each roll of the dice, regardless of what comes up, unless it's a double appears, and then you lose 5 points. If you gain 100 points within 36 rolls, usually with kids I say you will win a chocolate frog. I was going to be daring tonight, and So, you know, I'm sure TI will pop up for a brand new Inspire or TI84 or something like that, but then I thought that would be the time the laws of probability, there's always that outside chance, you know. But if we have a look at the simulator now, we're set up, and so now you can see a real example. And I can't actually see the chat window, but I'll ask Brian or Ray to keep an eye on it for me. And
have we got your simulator there, Jim?
Sorry?
Have we got your simulator there?
You should have now, have you?
Yeah,
I'm seeing a PowerPoint. Okay.
And you should see the simulator on top.
Yeah, I can see it.
Okay, yep, got it now.
Yep. Okay. So, yeah, you can imagine, just think of the reaction from this that happens with kids, is that, you know, 100 points from 36 rolls, that shouldn't be too hard to come up with. You know, you only lose 5 points if there's a double. So let's start rolling the dice, and, okay, you've gained 5 points. Oops, you've lost them again. Gain 5 points, and you've lost them again. Now, this is purely random, remember? Purely random. And you've gained 5 points, 10 points. Oh, you're back to 5, and so on. Oh, you're back to 0. You know, imagine what the kids are starting. It doesn't take too long for the kids to start to react to this, and so on. You guys that have got the audio, I might like you to think you might comment, you know, sort of things that kids might comment on there, or somebody out there and might like to type in the chat and sort of think about what the kids would be doing and so forth. And of course, you know, I have never given away a chocolate frog, right? And immediately the kids start talking about, you know, you've rigged it and so forth. And I obviously have, and that's part of the purpose of tonight, is to show you how we can so-called rig it with this app. But my challenge for the kids and what we do with this is to say to them, prove it. And then we have to have it. How would they say? Well, let us have a look at your, you know, software, your SmartView software. And no, it's mine. Prove it. And I've been known to get all indignant and take offence at being called a cheat and so forth, and tell them that if they want to make a complaint to me, they better write to the School Ethics Committee and back it up with data. And then they suddenly realise they've been conned, because that's their assignment, to produce a mathematical report with evidence to say that my thing was rigged and so on. So let's have a look at it now. If we press the escape and go out, you would actually see that we've got some more options there, and I can have a look at the graph rather than the table. So before, when we were simulating things, I had the table coming up. Here's the table now. You can see that there's something strange happening here. We're getting a lot more double sixes than one might normally expect for 2 standard dice. What I can actually do is that if the kids wanted to investigate this, we can export that data and to lists, so that even when I get out of the app, that data is still going to be there and kids can go through and analyse it and so on. I'm not going to go there at the moment. But the thing that we need to look at for you is that look at the set option. And this is where we can control the experiment that we're setting up. You can see that we can have 1, 2 or 3 dice, we can have 6, 8 and so on up to 20. We can graph the frequency of the probability, we can control what we store in the table and so on. And the other one is that in this advanced tab here, we can actually go in and set the probability. And you can see that in tonight's little activity, I've actually hideously biased it towards the 6. And just to indicate what's going on there, if I go down and change that, suppose I want to give you a fighting chance of winning a TI Navigator or something like that, I might change that back to 5, and as soon as I click enter, you notice that the probabilities change. And I can also, if I did it the other way, if I went over and changed the probabilities, and suppose I wanted that to be 0.3, then it would adjust the other probabilities. Notice that 6 just can't do it. It's got to have at least 0.1, and so it's balanced out the probabilities according to the changes that I've made. So it's quite a good little app there that we can look at. And just to finish off with one other example, just to talk about it, this is one that I've used in the current job I'm in, where we're looking at ways of extending students. This one's a little bit different. We've got a problem here that we call the lucky prince. Maybe he's not so lucky. Prince climbed the wall to meet the emperor's daughter and was captured, and he's given a chance to live. The emperor tells him there's 50 red marbles, 50 blue marbles, and 3 identical urns. He can place them in the urns any way he likes, but the urns are going to be rearranged. They won't change what's in them. He picks an urn and then reaches in to choose a marble from that. If it's red, he lives and gets to marry the princess. If it's blue, he dies. So how does he arrange the marbles to get the greatest chance of living? And I've done that as an extended problem with students through an entire unit of probability, where every day we picked another student and they have physically rearranged the marbles and so on in there and try to set it up. You can do it with the calculators. Kids working in groups with a few calculators each, they can go in and set it up accordingly. What I wanted to just show, just to finish off, I won't go through and set it up, just to finish it off, by the time you get through and you analyse the probability, that's the solution that maximises his chance. You put one of the ones that's going to guarantee he's going to live in each of 2 urns, and you put the rest in the 3rd urn, so that this one is guaranteed to live if he chooses this one. This one, he's got about a 50-50 chance if he chooses this one, and you can draw the tree diagram and work out the probabilities, and it comes out, when you work it out, that his chance of living is just a little bit over 80%. And the kids have a lot of trouble accepting that we could, you know, alter the probabilities by how we place the marbles in the urns to that extent. And so what we actually do is that we set up 2 calculators, and they can go away in groups and explore. One calculator is set up as a spinner with 3 options to represent the 3 urns, so which one is he going to choose, and then the other one is set up with the container with the marble that's obviously got 48 blue and 50 red ones in there, and then the kids can go through, and when they run it, too far, there we go. When they run it, they can generate, you know, at a couple of clicks of a button, 100 data sets, 100 data points, and go through and analyse that, and for each one of those, match it up with one of these and decide if he lives or dies and so on, and see that experimentally it does turn out to match the theoretical one. So a little bit rushed there on those, but I guess the message tonight is that there is so much potential in these apps that you just need to get in there and play with them and see what they can do. You will find options in there and think about ways that you can use them with your students and come up with ways to either make it, or not either, do all of these, make it interesting, make it more enjoyable for the students, save time. All of these things are possible by using these apps. And so I encourage and hope that you will get in there and have a play. And as we said, there's quite a few others available that you can load into these calculators and see what you can do with the students. How's that for time? Brian, how are we going? not too bad. I'll hand back to you.
So, yeah, thank you to both presenters for the wonderful ideas they've shared there, and thank you, participants. In my capacity as host, I've been watching you hard work there, and I've decided that you've all passed, and you will be receiving a PD certificate shortly in your email. Also, as a follow-up from that, you will have links to be able to download PowerPoints and some slides presented by the presenters. You can also watch this, you can download the entire webinar from the TI website, or see it, or bits and pieces thereof, on our YouTube site. There it is. And all we ask in return is the feedback. You're allowed to say things like, the host did a wonderful job as well, you know that. And if you, webinars are great, but if you want to see a face-to-face professional development, here are some upcoming Learn and Energize Connect PD days at Ringwood, Warrnambool and Mount Waverley. Or if you're in Queensland, far north, Cairns, it's almost worth a trip to Cairns just for that. Or at the QAMT. So that's where we are. Thank you again to all our presenters this evening. You've been listening to Jim Lowe and Ray Cross, and all the best from all of us, and good evening.
Good evening.
Thank you, Brian.